Italy, I work for the Italian Space Agency in the Deep Space Observation and Exploration Unit. Today I will talk about orbits and their properties, so orbital dynamics. For example, we want to move from one planet, the Earth, to another. The bodies involved are many. For example, from Earth to Mars, so we must consider the spacecraft, the Earth and the Moon, the Sun, Mars. So this is a four-body problem that cannot be solved in an analytical way and cannot be solved without a lot of numerical computing. But what we can do is to split this large problem into little problems. So we split into what we consider just two-body problems, neglecting the other ones for a short time. This is an approach called patched conic approximation. So in general we can consider the interplanetary trajectory into three separate regions and consider the gravitational attraction on the spacecraft from only one body at a time in each region. Now, if we want to leave the Earth, this must be done on a hyperbolic orbit. There is an open path that brings the spacecraft away from the gravitational sphere of influence of the Earth. So at that point, when the spacecraft goes out of the gravitational sphere of influence of the Earth, that is the region where the Earth is the major body influencing the motion of the spacecraft, we enter in a second phase where the Sun is ruling the dynamics, and at that point we have an orbit centered around the Sun. Then we reach the gravitational sphere of influence of the target planet, and we enter this sphere and we arrive at the target planet with an hyperbolic trajectory. So, escaping from the Earth's sphere of influence, this for the Earth is around 1 million kilometers. Now, if we consider the reference frame centered in the Earth and the spacecraft is initially in a circular parking orbit around the Earth, we have to exert an initial delta V, so to place the spacecraft into this hyperbolic trajectory of escape, and the velocity it reaches at the exit of the sphere of influence can be considered the asymptotic velocity, the v infinite. Now, if we recall that energy is saved in considering only the gravitational field, the energy we have at the pericenter, it must be equal to the energy we have at the infinitive, that is for us at the exit of the sphere of influence. So we have the sum of this potential energy plus kinetic energy must equal in these two places, and we can neglect the potential energy at the exit of the sphere of influence because the radius is very large, and we can get the velocity that is needed at the velocity that is needed at the pericenter of the hyperbola to reach that infinitive asymptotic velocity. And from that we can compute the delta V required. That will be the pericentric velocity on the hyperbola minus the circular velocity on the parking orbit. What we must pay attention to is the fact that the asymptotic velocity is very sensitive to small errors in the initial velocity at pericenter. In fact, if we differentiate the expression for the asymptotic velocity, we can see that the relative error in the delta V at pericenter is amplified by the ratio of V0 over V infinitive. Just to give some numbers, to obtain an asymptotic velocity to reach Mars of 2.98 kilometers per second, we must reach a pericentric velocity of 11.6 kilometers per second. The asymptotic velocity at the exit of the sphere of influence will be the relative velocity of the spacecraft with respect to the Earth. This means that this will be added in a vectorial way with the velocity of the Earth with respect to the Sun. Now, just to give some numbers, for example, for a Mars mission, if we start in a parking orbit around the Earth, let's say 400 kilometers, we apply a first boost to enter hyperbolic departure trajectory with respect to the Earth. Then, when we exit the sphere of influence of the Earth, we travel on an elliptical transfer orbit, sun-centered, that takes us to Mars. Of course, this must take into account the phasing so that we reach the orbit of Mars when the exact time when Mars is in the exact position. When we get to Mars, we are again on a hyperbolic trajectory with respect to Mars, since the velocity with respect to Mars will be the difference between the velocity with respect to the Sun and the velocity of Mars. So the relative velocity will be our asymptotic velocity at entrance at the Mars sphere of influence. At that point, once we get at the desired distance from Mars, we apply a second impulse to slow down with respect to Mars, so entering an orbit that is centered around Mars. Just to have an idea of numbers, in this case we have a delta V at boost exiting the Earth sphere of influence of 3.58 kilometers per second, while to enter Mars orbit we need another 2.10 kilometers per second. So this sums up to more than 5 kilometers per second of delta V. And the time of flight just for this simple Oman transfer is 259 days. So just to understand how a gravity assist works, I would like to show you this small comic. Suppose that we have a planet that is moving with respect to us, and that we throw a baseball on the front of the train. The train is moving 50 miles per hour, and we throw the ball 30 miles per hour. Now, just try to think yourself how much will be the velocity after this impact. What you would think is an easy answer, maybe 50 miles per hour plus 30 miles per hour, is not correct. actually to see how to solve this problem, you must put yourself in the situation of the train conductor. The train conductor in his reference frame sees the ball coming towards him with a velocity that is the sum of the two velocities. So is actually is 30 plus 50 in this frame. So when you have consider an elastic impact, the same velocity will be reflected. So you would have 80, but 80 with respect to the train that is moving itself 50 miles per hour. So the right answer is 130. So this is to say that how gravity assist works, because when you pass near a planet, you can obtain, you can exchange energy with the planet and obtain a variation of your speed, your velocity, as a bonus without using your propulsive system. So passing in the back of a planet, you may see that you have a certain velocity with respect to the Sun, and you have a planet velocity with respect to the Sun. Then the relative velocity will be the difference between these two vectors. At that point you are on a hyperbolic path with respect to the planet. At the exit of this hyperbola, your relative velocity vector will have rotated and will add again in a vectorial way with the planet velocity, obtaining a new velocity vector with respect to the Sun. So if you pass behind a planet, you end up increasing the speed relative to the Sun, while if you pass in front of a planet, you may decrease the speed relative to the Sun. And this is a technique that is commonly used in interplanetary missions to obtain orbits that otherwise would be impossible or would require huge amounts of propellant. So in the end, where does this free energy come from? Of course, you can get something for nothing. The spacecraft slows down the planet or accelerates the planet. So the exchange of energy between the spacecraft and the planet, since the energy saves, what the spacecraft gains is lost by the planet. But how much does the planet slow down? For example, the Galileo spacecraft that was launched to study Jupiter gained about 9 kilometers per second from two subsequent gravity assists from the Earth. And this has slowed down the Earth, but how much? You may see 0.13 meters in 1 billion years. This is the kind of deceleration. Of course, the two masses are so extremely different that the effect on the Earth is much less observable than on the spacecraft. So this ends my talk. Thank you very much for your attention, and all the best.